Hi, and welcome back to Statistics Online. Today's lesson is the Central Limit Theorem. And the Central Limit Theorem, in particular, informs us about the shape of the sampling distribution for the mean. So recall, the sampling distribution for the mean is simply if I'm taking repeated samples from a population, and each time I take a sample of a certain size from that population and calculate a sample mean, a statistic, if I gathered all those possible sample means, drawn from that population and organized them, then that distribution would have its own shape, its own center, and its own variability. And the central limit theorem is going to inform us of what the shape of the sampling distribution for the mean is. The first point is that if the population data set is distributed normally, then the sampling distribution will also be normal. This isn't the central limit theorem. This is just a property, that if and it should be sort of intuitive, that if the population itself is bell-shaped, then any distribution, of statistics gathered from repeated samples taken from that population will also be distributed normally. This condition is important, but it's limited in the case that often in inferential statistics, we're not going to know what the shape of the underlying population is. Because to really know the shape of the underlying population, you need the population. And of course, if you have the population, then you don't need to do any inferential statistics. And so it's the second point here that is the more important. Now, if the population distribution is unknown, that's very practical, or known to be abnormal, which could be also practical in the sense that we know a lot of data are going to be skewed, grades, income, these kind of data sets. Even if we don't have the actual population data, we have intuition about which way they're skewed, and certainly they're not normal. But anyway, regardless of how the population is distributed, provided that the sample size is large enough, that little n is large enough, then we can rely on the central limit theorem. The central limit theorem will tell us that the distribution will be normal. So let me provide the definition here, the central limit theorem. Regardless of how a variable x is distributed, again, this x could be anything: income, weight, height, speed, volume, GPA, miles per gallon, revenue, profits, costs, marginal values, anything, any variable that we're treating here as continuous, regardless of how it's distributed in its population, the sampling distribution of the means will be distributed normally for sufficiently large samples, and sufficiently large means n greater than or equal to 30. So to give you an example, let's say that we had a population data set that was dramatically right skewed. For instance, this could be income. And it had a mean that would denote as, of course, mu, the population mean, sub x, just the income. And we were our notation for the standard deviation of the population, sigma, lowercase sigma. Again, that's the population standard deviation. Now, if I was to take repeated samples from this population that's right skewed, repeatedly sampling, and as long as my sample size is greater than 30 or greater than or equal to 30, so let's say it's 45, just for example. If I were to take all possible samples of size 45 from this population and calculate x bar, then my distribution of x bars, also in income, would be my sampling distribution. And the point is that it would be centered at the same value as the population mean, but it would not be right skewed. It would be normally distributed. And moreover, the standard deviation of this distribution is called the standard error. and it is the following. So now we have all properties of the sampling distribution for the mean, right? We know that the sampling distribution for the mean is going to be normal by the central limit theorem as long as the sample size is big enough. We also know that the mean of the sampling distribution equals the population mean. And third, we know that the variability of the sampling distribution is strictly less, okay, than the variability from its population. The standard error is less than the standard deviation of its population. And the formula is simply the standard error of the population divided by the square root of n. So as n goes up, as my sample size goes up, we should expect a distribution that's tighter and taller around its mean. To summarize, there are two ways the sampling distribution of the sample means will be normal. The first is the more limited case when the parent population is normal. This holds for any sample size. And the second point is that the sample size is large enough, right? And if n is 30 or more, then we can rely on the central limit theorem. Here's an example of the central limit theorem. I'm not going to be able to draw all possible samples of a certain size from a population, but I do a partial sampling distribution. You can see how the shape tends towards normal. So in this example, I have asked students, quite a few students from one semester, 258, how many movies they have seen that star Tom Hanks. I picked Tom Hanks because he's been in a lot of movies, and so we could get some variability. And so these 258 students answered my survey question, and the population mean is, and so my population is 258, and my population mean was 10.64 films. So on average, a student in the population watched a little over 10.5 films that starred Tom Hanks. Now, using Excel, I took random samples of size 30. Okay, so I'm going to be pulling samples of size 30 from this, and I do different quantities of these samples of size 30. I'll show you that I'm going to do 30, 60, 150, 200. I'll show you graphs of some of those. And I'm taking the mean of means from these samples just to illustrate how these things change. So for this first bullet point here, or this sub-bullet point, when I took 30 samples of size 30 and calculated the mean of means, I got 10.93, which of course is different from the population mean. It's not too far off, but different. I took 60 samples of size 30, 150, 200 samples of size 30, for instance. My mean is 10.7, and it's not quite the population mean, but again, not too far off. And this question here in blue, if I take all possible samples of size n equals 30, what will the mean of means equal exactly? And hopefully, you can answer this question now that the mean of all those sample means will exactly equal 10.64. It will exactly equal the population mean. Now, how many possible samples of size 30 could I take from this population of 258? Well, my calculator and Excel program couldn't figure that out. We're talking millions upon millions of samples here, okay? Taking 30 from 258. And so I'm not going to be able to do this. And, I think that 120 is a... There we go. Sorry about that mistake. So we don't know this number exactly, but we know that there are a huge number of samples. So here's the population data set as a, well, it's a frequency distribution, but it would be the same as a probability distribution if it was a relative frequency. You know, if I took each bar and divided by the total, then we'd be in probability terms. So the shape is the same. It's something right skewed. You can see that over here. Somebody reportedly watched more than 55 movies starring Tom Hanks, which I don't think is even possible. But this is what you'd call the Tom Hanks superfan, maybe to an alarming extent. The rest of these people are over here, it is right skewed even without this outlier, maybe not dramatically so, but is right skewed. So the population isn't normal, but let's see what the repeated samples drawn from that population, the shape of those distributions look like. And so here's the first 30 sample means of size from samples of size 30, so I only have 30 observations here. Now let's look how this changes when I move up to 60. You can see that it's starting to take on more of that symmetric bell-shaped curve, and I have spaces in between these bars just by a matter of aesthetics. Here's the 200 samples of size 30. And so what you're seeing here, is that as I am approaching a full sampling distribution for this mean, we're watching the central limit theorem at work. The central limit theorem says that these sample means are going to be distributed normally. If I keep adding 200, 600, 700, 2,000, 500,000 sample means, it's going to be a pretty smooth distribution. And so that's the central limit theorem. Okay, let's look at some example problems for calculating probabilities under a sampling distribution for the mean. This first problem says that a large statistic class has 150 students in it. And so consider this class as the population of interest. That's our population. And suppose the mean grade for quiz 1 in that class was an 80% with a standard deviation of 5 points. Now suppose that I, Dr. McAvoy, drew a sample of size 40 from that large class and computed a sample mean. I computed X bar. Okay? Here's the question. What is the probability of myself, of Dr. McAvoy, obtaining a sample mean of 82 or greater from the population? Okay, so towards answering this question, we first have to ask ourselves, is the true sampling distribution of a sample size of 40 normal? And the answer is yes, because the sample size is 30 or greater, so we can rely on the central limit theorem, CLT. So we know that we can draw this bell-shaped distribution. What awesome table have we used in the past to find probabilities under a normal curve? Well, we're free to use the z-table. The beloved z-table. But consider what the formula for the z-score looks like now, okay? Because we're looking for a z, a standardized value, but the standard deviation of the sampling distribution, also called the standard error, is a new part of that formula. So look at z, the numerator is the difference between my sample mean relative to the population mean, okay, the mean of all possible means, over the standard error, which is the standard deviation of the population divided by the square root of n. If students get this section wrong, it's typically because they're dividing by the population standard deviation rather than correctly dividing by the standard error. And this is important because we're not talking about a distribution from the population. We're talking about a distribution of sample statistics drawn from that larger population. So, this is the z formula. I'll again pause this. All right. So again, the question is, what's the probability of taking a sample of size 40 and getting a sample mean of 82 or more? And again, we have our population mean of 80, the standard deviation of that population of 5, and n is 40. We know that the shape of this distribution is normal, even though that, let's try that again. Better. Okay. It's centered at 80, the mean of sample means equals the population mean. However, the standard deviation of this distribution is not 5. It is sigma x bar, which is 5 divided by the square root of n, 40. And the standard deviation here is 0.7906, so about 0.8. Alright, so one standard deviation above the mean would be 80.79. 2 standard deviations. Anyway, as we get to 82, just somewhere here, let's say 82, and we want to know what this area here is in red. All right, and so that requires a z. So the appropriate z is what is, the numerator is 2, right? But the denominator is 0.7906. It's going to tell me how many standard errors, how many standard deviations of this distribution is away from the mean. And it 2.53 is the answer there. And if I look up 2.53 on the z-score, on the z-table, and subtract that area from 1, the answer to this problem is 0.0057. So about 0.6% of the time am I going to get a sample mean of 82 or more. And so think about it. 82 in absolute terms is pretty close to the population mean of 80. It's only 2 percentage points away. But in terms of a sample of size 40, the likelihood that I get a sample mean 82 or more is pretty small, 0.0057, or about 0.6% of the time. Let's look at this other question here. The age of newly tenured professors is normally distributed with a mean of 40 years and a standard deviation of 3 years. What is the probability that a sample of 16 newly tenured professors will yield a mean age of 43 years or more? So a sample size of 16 is not big enough to appeal to the central limit theorem, but I want to point out through this example that we didn't need to rely on the central limit theorem here. The population here is told, you're told that the population is normal, so this is bell-shaped, and so any sampling distribution pulled from that population will be normal, regardless of the sample size. Okay, so we know that this is going to be a normally distributed distribution of sample means as well. All right, and so towards answering this question, we'll draw the normal curve. This is going to be x bar. This is in years. The population mean is 40, so the mean of all sample means will be 40. The standard deviation of the population is 3 years, but the standard deviation of the sampling distribution is 3 divided by 4, the square root of 16, and so 0.75, 3/4. Right? And so 1 standard deviation above the mean would be 40.75, 2 would be 41.5, and so on. And if I'm after 43, which is somewhere out here, we'll quickly see that the z-score for 43, which was a numerator of 3, divided by 0.75 is going to be, in relative terms, a huge number. It's 4.0. And in fact, the z-table only goes up to 3.99. So the probability of taking a sample of 16 professors and having their mean age 43 years or more is statistically 0. All right? At some decimal place out, we'll get a positive number. But in terms of what we know, this is 0. Okay, so it's effectively 0. And finally, we have an example here that the waiting time for from airplane taxi to takeoff is known to have a skewed right distribution. Okay, so it's not normal. With a mean of 10 minutes and a standard deviation of 8 minutes, 100 flights have been randomly sampled. So n is going to be 100. Describe the sampling distribution of the mean for these 100 flights. Well, to answer this question, we have to ask, what are the 3 properties, right? Is it going to be normal? It is going to be normal because, not that the population is normal, we know the population is right skewed, it's normal because of the central limit theorem. As long as n is 30 or more, we can safely say that the distribution will be normal. So it's normal. It has a mean equal to the population mean. But does it have a standard deviation equal to the population standard deviation? No. The standard deviation of the sampling distribution is the standard error, and it's sigma divided by the square root of n. So the only answer that satisfies the three properties of the distribution is 2. It's normal, mean equal to 10, and standard deviation equal to 0.8.